Okay, good morning, everyone. Hope you're well. We are carrying on today with our new theme on open challenges in the field of evolutionary robotics. Before we get to that, you are now working on assignment 9, which is the parallel hill climber. This is, I think, arguably the longest. This is the longest assignment you're going to tackle. So as always, please start as soon as you can on assignment 9. As the name implies, and as we've talked about before, the parallel hill climber is not conceptually that distant from the hill climber, which you just implemented. In this case, you're going to be developing a population of parents. So we're now moving to population-based search methods. A population of parents at each generation. Each parent produces a randomly modified copy of itself. So each parent has its own child solution. We evaluate all of the child solutions and we then march down the population and we run basically the hill climber. So one tricky part in this is you're going to be actually running this in parallel on your laptop or desktop. So depending on how many cores you have on your machine, your parallel hill climber will run faster or slower. If you haven't worked with running parallel processes before, that takes a little bit of time to wrap your mind around. So again, leave yourself plenty of time to work on assignment 9. Another thing that came up this week about the hill climber is obviously when you're running PyBullet in direct mode rather than GUI mode, you're not seeing the graphics, but PyBullet still is sending out warnings and error messages, which are getting mixed up with the printouts of the fitnesses, and it can be a little bit, your screen gets a little bit busy. A lot of things are being written to the console. Some of you have solved that by running search.py in the Python IDE, the idle editor. I think that does the trick. And there's a suggestion down in here somewhere about how to do this if you're on a Mac. Let me see if I can easily find this. It's in here somewhere. You can go and have a look for it. But if you are getting those PyBullet warning messages, you can just ignore them. As long as you're running your hill climber and getting something that starts to move to the left and away from you as the observer, you're good. Any questions about the hill climber, parallel hill climbers, assignments, anything else before we push on? All good? Okay. All right. So we started last time by introducing the first challenge in the field of evolutionary robotics, this concept of modularity. Or maybe a better way to say this is the challenge is non-modularity. We're going to see, actually in the next lecture, we're going to see if you start to allow evolution to not just tune the weights of synaptic connections between neurons, but you allow the evolutionary algorithm to start adding and removing synapses as well. Evolution will tend to produce increasingly non-modular neural networks. It will start to wire up every neuron to every other neuron, which, as the engineering disciplines have learned, is not a good thing, not a good way to build things. If you have a very non-modular system, making any one change tends to break everything else. So how do we go about evolving good solutions that are also modular solutions? That's what we're going to look at today. And we're going to focus mostly on structural modularity. So looking for dense connectivity between one set of neurons that are not wired up as much with other neurons or other parts of the neural network. Okay. There's two ways we can do this. We can either tell the evolutionary algorithm what the separate neural modules should be, or better yet, allow the evolutionary algorithm to make modules inside the neural network. The latter approach, although a little bit more difficult to set up in code, has the advantage of overcoming the problem of thinking about thinking is misleading. What we think may be subtasks in a particular task are not the best way to carve that task up into subtasks from the point of view of the robot. So to better ground this idea, I'm going to introduce this distinction between distal perspectives of behavior and proximal perspectives of behavior. Let's start with distal perspectives. So if we are observing an animal, or in our case, observing a robot, we are observing that robot's behavior from a distance. And we may make assumptions about what is going on in the head of the animal, or better yet, in the head of the robot. This problem of distal perspective was actually a huge deal in animal behavior back in the 1950s, and was sort of controversial because, again, if you observe an animal, you may attribute things that are going on inside the head of the animal that are not happening there. We saw Valentino Breitenberg's vehicles a few weeks back. Valentino pointed out that what's going on in the mind of a fruit fly is probably very different from what people thought. And these erroneous assumptions come from taking the distal stance. Here's a very simple example. Imagine we have a wheeled robot and it has 5 distance sensors. And at one point in time, this robot is driving past a cylinder. We're looking down on the top of the cylinder and down on the top of the robot. And we would say, if we were asked to describe what the robot is doing, it's driving past the cylinder. We can see that the beams, two of the five distance sensors are registering the cylinder. So the robot is driving past the cylinder. The robot can see the cylinder. Okay. Same robot at some short time later, maybe it's driving past a block, and again, two of the 5 of its distance sensors are registering the object. We would say the robot is driving past the block. And we might just assume, of course, in these 2 different instants of time, the robot can distinguish between these 2 objects. But if we now change our perspective and try and put ourselves in the shoes of the robot and see through the robot sensors, we see a very different situation. If we take a proximal perspective or a proximal stance, proximal meaning nearby or close, we are now seeing things through the robot's eyes. We notice that at these 2 instants of time, if the only thing the robot has is these 5 sensor readings, and then some short time later, these 5 sensor readings. Assume the robot has no memory, can't remember. The robot cannot distinguish between these objects. We can, because we're looking at these objects from the outside, but we're looking at them differently from the way the robot is looking at them. This is just a cartoon example, obviously, but this comes up a lot in robotics and the study of animal behavior, and often leads investigators in the wrong direction. Rather than us imposing what we think the robot should be sensing or doing under certain circumstances, it would be greater if we allow evolution to come up with solutions where evolution can only work with the raw materials produced by the robot, which are the robot's sensor signals. Okay. So we're going to look at this is an early study from evolutionary robotics that tackled this issue of trying to evolve modular solutions or modular robot behaviors. They used the Kepra robot, which we've seen before. And the Kepra robot in this experiment, it has 2 wheels, and it's been equipped with a gripper, and you'll notice that in the gripper it's holding a little sugar cube. So the question we're going to ask of the Kepra when we're going to start to evolve behaviors for this robot in a moment is how to enable an evolutionary algorithm to discover modules appropriate to the task. What's the task? The task is for this Kepra robot to move around on the top of a table, and we're going to place 5, or the investigators placed 5 objects on the top of this table. The robot has to drive around, find these objects, pick up one, take it to the edge. It's in an arena, not on the top of a table. There are walls here. It's a walled arena. The robot should pick up an object, drive to the wall, and drop the object over the wall and out of the arena. This robot has 6 infrared sensors emanating from the front of it. So again, these distance sensors. And it has 1 light barrier sensor, which is basically a laser going from one pincer to the other inside the robot's gripper. So if that light barrier sensor is broken or registers a low value, that means the robot is holding an object. The light barrier sensor, if that beam is unbroken, the sensor registers a high value and the robot knows that it is not carrying an object. Okay. So those are our 6 sensors. The robot has 4 motor neurons, and like we've seen many times before now, one of the motor neurons is going to control the speed of rotation of the left wheel. The other motor neuron is control the speed of the the right motor. The third one is going to trigger object pickup, and the fourth one is going to trigger object release. So what does that mean? Imagine we have these 4 motor neurons, and as you now know, these 4, at any given point in time, these 4 motor neurons are emitting 4 floating point values. At each moment in time, we look at these 4 values and we look to see which one has the highest magnitude. Whichever neuron has the highest magnitude, that's the one that's in control. So if the third motor neuron has the highest magnitude, the robot will make this motion. If the fourth motor neuron has the largest magnitude, it will trigger the robot to do this. If the robot is already in this position, it will stay in this position. If the first motor neuron has the largest magnitude, we look at the magnitude of that value, and that becomes the speed of the left motor. If the second motor neuron has the highest magnitude value, we take that value and control the speed of the right motor. Okay, a little bit different from what we've seen before, but not that different. Okay, if you think about this task, pick up all the objects and drop them over the wall and out of the arena, you can imagine different ways of carving up this task into different subtasks. Here's one way in which we carve it up into 1, 2, 3, 4, 5, 6 different subtasks. First subtask is explore the environment and avoid the walls. You can imagine creating or setting synaptic weights to create a more or less simple Bratenberg vehicle that will turn away from strongly firing left infrared sensors, and it will turn to the left if the right infrared sensors are firing strongly. So that's A. If the robot happens to be near an object, recognize that object and move into position to pick it up. Third subtask, pick up the object. Fourth subtask is drive towards the closest wall, assuming you're holding an object. Fifth subtask, recognize wall, move close to it. And the 6th and final subtask is release the object. You can guess from all this build-up in this lecture so far that this is not the way evolution is going to carve up this task when we give the evolutionary algorithm the ability to carve up this task. We'll talk about it in a moment. You could imagine a different decomposition, which is look for and grab objects and go and get rid of objects, 2 subtasks. Right? Different ways we could carve this up. What is the appropriate way to carve up this task from the point of view of the robot and the evolutionary algorithm? Okay. I like this particular study because the investigators sort of snuck up on this problem. They performed a number of evolutionary runs, which we're going to see in a moment, and they performed these evolutionary runs with a series of increasingly complex neural networks. So in all cases, we have the same robot, same 6 sensors, same 4 motor neurons, different neural networks. Neural network A is the simplest one. We have the 7 sensor neurons down here, the infrared sensors and the light barrier sensors. The investigators are Italian, so this is light barrier in Italian, which I don't remember what it is. That's why it's BL and not LB. We have 7 sensor neurons, and here's our 4 motor neurons. You'll notice that each sensor neuron is wired up by a synapse to each motor neuron. There are no hidden neurons. There are no recurrent connections. There are no self connections. This is pretty much just one step up from a Bratenberg vehicle. Pretty straightforward. Okay, we'll see some results of evolving the robot to try and clean up the arena with neural network A in a moment. They then performed another set of evolutionary runs with neural network B, where it's the same as A, except they introduced a hidden layer. Each sensor neuron is wired up to each motor neuron, and each motor neuron is wired up to each motor neuron. No recurrent connections, no self-connections. What is the potential advantage of network B over network A? What do hidden neurons buy you? What do they buy the robot? Remember back to our original lecture on neural networks. When we were looking at neural networks that compute the AND and the OR and the XOR function, what's the advantage of a hidden layer? So Alex has already mentioned exclusive OR. So the hidden neuron, in those examples, the hidden neurons allowed the neural network to compute a function that was beyond the ability of any feed-forward network that had no hidden layer. What is it about what is different about the exclusive OR function compared to AND and OR? I think we mentioned this at some point. The exclusive OR function is a non-linear function. AND and OR are linear functions. So a complex enough neural network can compute any function as long as it has some hidden neurons in there. So network B would allow the robot to perform a nonlinear transformation of its sensor values into motor neuron values. Whether or not nonlinear transformations of sensation into action is useful, we don't know whether that's useful in this task. But if we evolve robots with network A and then we evolve robots with network B, and the evolved B robots consistently do better at the task than the evolved A robots, that will provide us with proof that whatever the robots are doing, they need to perform a nonlinear transformation of their sensor values into motor values. Okay, that's just kind of an aside, not so important for our purposes. That's covered in much more length, in much more depth in neural networks courses. Okay, network C has 1, 2, 3, 4 hidden neurons in it. And this is drawn a little bit differently. We've got our 1, 2, 3, 4 hidden neurons, and you'll notice that hidden neuron 1 has a recurrent connection to hidden neuron 3, and hidden neuron 2 has a recurrent connection to hidden neuron 4. So it's kind of an odd way to draw the hidden layer and recurrent connections, but you basically get the same thing. In network C, we have hidden neurons. And recurrent connections. What do recurrent synapses buy you? Or again, what do they buy the robot? Hidden neurons allow for nonlinear transformations of sensation into action. What's the potential advantage of recurrent synapses? Logan says memory, exactly. Is it important in this task for the robot as it's going about and cleaning up the arena to remember past sensor values? Maybe, maybe not, hard to say. Again, if we evolve C robots and they consistently outperform the evolved B robots and evolved A robots, then we have our answer. Memory is useful. Okay. Network D is going to look quite different from any neural networks we've seen so far. This is the investigator's attempt to introduce their own modularity. In this case, the investigators looked at this task and they broke the task into 2 subtasks. What the robot should do when its gripper is empty and what the robot should do when the gripper is full. You'll notice here that the investigators are not assuming what the robot should do when its gripper is empty or what the robot should do when its gripper is full. That they're going to leave up to evolution. But they are imposing modularity. They're breaking the task into 2 pieces. And you'll notice, if you look carefully, there are two networks in here. One network takes all the sensor values and sends them to this set of motor neurons. The second neural circuit, again, takes all sensor values and sends them to these 4 motor neurons. If the robot's gripper is empty, these 4 motor neurons take control of the robot. If the gripper is full, these 4 motor neurons take control of the robot's behavior. Okay, so again, it's the investigators that are inducing the modularity. They're saying what the modularity is, but they're not telling the robot what it should do when it's in these 2 different circumstances. It's leaving that up to evolution. So during each time step of evolution, during each time step of evaluation of a given D network on the robot, all 8 output neurons here have their own floating point values, but only 4 of those 8 values are actually being sent to the motors. Make sense? At different points in time, when the gripper goes from empty to full or from full to empty, these different subsets of motor neurons take control of the motors. We've actually seen a neural network already from the 80s, actually, or maybe actually from the early 90s. We've seen a neural network that did something similar, that depending on what the robot sensed, different parts of the robot's brain or different parts of the robot's neural network would grab control of the motors. Does anybody remember what that network was? What it was called? That network was invented by Rod Brooks, who was at MIT at the time. Shortly after inventing this network, he left MIT and founded the iRobot Corporation. And iRobot is the producer of Roombas. So if you have a Roomba vacuum cleaner at home, the network that we're talking about now is what's running your Roomba. Anybody remember what that network was called? This was the subsumption architecture. Different parts of the network would subsume or take over control of the robot depending on its circumstances. Okay. So this is network D. We're now going to look at the 5th and final network, network E, and this network takes a little bit to wrap your mind around. This neural network is designed to allow evolution to carve up the task into subtasks if it wants to. So first of all, evolution is going to have the option about whether to evolve modularity into the neural network if it wants. And if it does, it's going to have the ability to carve up this subtask in different ways. So let's have a look at how they did this. Let's start with the input layer. That looks familiar. We have our 7 input neurons, our 7 sensor neurons down here. And we have 4 neurons allocated for each of the 4 possible actions. Left motor, spin the left motor, spin the right motor, pick up, or release. You'll notice there are black neurons in the back here and white output neurons in the front here. Let's talk about the selector neurons here. You'll notice there's a pair of selector neurons for each of the 4 possible actions. You'll notice that there are synapses that are flowing from each sensor neuron to each selector neuron and to each output neuron. At every point in time, we can query the the first thing we do is we query the sum of these pairs, the sum of the pair of these selector neurons, and that gives us 4 floating point values. Whichever of these 4 has the highest value, that's the action that the robot's going to perform. Let's imagine that this pair of selector neurons has a higher sum than this pair, or this pair at a given time. We then zoom in and look at these 2 floating point values. If the value of the left selector neuron is greater than the value of the right selector neuron, then the left output neuron controls the left motor. If the right selector neuron has a higher value than the left selector neuron, then this output neuron controls the robot's left motor. Okay, so here's one. If we look at this output neuron, we can see a whole bunch of synapses arriving here. This is one neural module. And if we look at this second output neuron here, there is a second neural module that is composed of all of the synapses arriving at this output neuron. So we have two different neural modules. And by evolving the synaptic weights that go from the sensor neurons to the selector neurons, evolution can tune which of these two neural modules controls the left motor under what circumstances. Okay, takes a little bit of time to absorb that. Any questions? Okay. Let's build up our intuition for network E here by imagining some hypothetical situations. Let's imagine evolution proceeds and is tuning is evolving all of these synaptic weights and produces a robot that does a pretty good job of cleaning up the arena. And when we look at what's going on in terms of the selector neurons, we notice that at every single time step, while the best robot, for example, the one with the highest fitness, is cleaning up the arena, this selector neuron is always, the value of the left selector neuron is always greater than the value of the right selector neuron. And the same thing in here, this value is always bigger than this value, this value is always bigger than this value, and this value is always bigger than this value. So there is never any switching between this module and this module. There is no switching between this module and this module. Hopefully that makes sense. That means that in this particular evolved network E, there's no real neural modularity. The robot is never using different neural modules. The selector neurons are never outputting values that cause switches between different neural modules. Let's imagine a different hypothetical situation. Let's imagine that when the robot is driving around, let's imagine we evolve a successful robot that cleans up the arena. When we watch that successful evolved robot in action, we notice that whenever the robot is not, when its gripper is empty, whenever it is not holding an object, the left selector neurons are always higher than the right selector neurons, meaning the robot's behavior when it doesn't have an object is being controlled by this neural module, this neural module, this neural module, and this neural module. But the moment the robot grabs an object, now suddenly the selector neurons switch. Suddenly this value becomes larger than this value becomes larger than this value becomes larger than this value, and this value becomes larger than this value. That means that when the robot is holding an object, it is this neural module and this neural module and this neural module and this neural module that's in control. That evolved E network is modular. Evolution has evolved different neural modules to control the robot when it's in different circumstances. Okay. I put a question down here to, again, hopefully help you build up an intuition for network E. We can ask how many states of this network are possible. We haven't really talked about network states before. It didn't really make sense, but now it starts to make sense. If we imagine a state as which selector neuron within a pair is in control, we have two states here. Either the left selector network is in charge or the right one is. Imagine we denote those two states as 0 or 1. 0 means this one is in charge. A 1 means this one is in charge. So 0 or 1 here. We can imagine 0 or 1 here. We can imagine 0 or 1 here. And we can imagine 0 or 1 here. In the hypothetical network E that I just talked about, where the left selector neurons are all have larger values when the gripper is empty, that's 0, 0, 0, 0. When the robot grabs an object, it switches to 1, 1, 1, 1. Yeah? That's just one example. There could be another situation where the robot drives around, and when it's away from a wall, when it's far from a wall, we have 0, 0, 0, 1. When the robot gets close to a wall, it's 0, 0, 1, 1. You can imagine a different change. How many possible states or how many different combinations of neural modules can control the robot? If we imagine each of these four groupings as having binary states, either the left neural circuit is in control or the right neural circuit is in control, how many possible states are there? As Ben mentions, there's 16 possible states. Okay. Last aspect of this I want to talk about. As you can see, again, there are synapses that are going from the input layer to the selector neurons, and there are also synapses that are flowing from the sensor neurons to the output neurons. If a mutation alters this, if a mutation alters one or more of the synapses going from the sensor to selector neurons, how does that influence the robot? What change has that mutation introduced into the neural network and potentially into the behavior of the robot? If it helps, think about many mutations. Let's just ignore the output neurons for a moment. Just imagine evolution proceeding, and evolution is altering the synaptic connectivity, the influence of the sensors on the selector neurons. What is evolution doing in that case? If it's not clear, let's turn this around. Let's ignore the selector neurons for a moment and just focus on the synaptic connectivity between the sensor neurons and the output neurons. As evolution proceeds and the weights of the synapses from sensor to output neurons are altering, how is that affecting the robot? How is that affecting the robot's behavior? That should be more familiar. We've talked about this many times now. Altering synaptic weights between the sensor neurons and the motor neurons. What does that do? It alters how the robot acts in response to its sensor values, right? So depending on the infrared sensors and the light barrier sensor, it determines what the robot will do. Maybe when it gets close to a wall, all infrared sensors become shortened. The robot fires its left motor or attempts a release operation, depending on how these weights are set. We're influencing the robot's behavior when we're evolving or altering the synaptic weights from sensor neurons to motor neurons. What are we altering, or what is evolution altering when we're altering the weights of the synapses that go from the sensor neurons to the selector neurons? We may be indirectly influencing the robot's behavior, but what are we changing, or what is evolution changing? If you want to unmute yourself and offer an opinion, that's fine too. No? Okay, let's go through this. So synapses that connect the sensor neurons to the selector neurons, if we alter those if we alter those weights, it's going to alter how and under what conditions the selector neurons change values, or how the sensor neurons influence changes at the selector layer. And change in values at the selector layer is going to change or switch or select which neural modules are controlling the robot's behavior. So by tinkering with those weights, sensor to selector, evolution is playing with or trying out different forms of modularity. What if a subset of these neural circuits control the robot when its gripper is empty or its gripper is open? What happens if we switch between neural modules when the robot is far from the wall or close to a wall, or close to an object or far from a robot? Altering those sets of synaptic weights allows evolution to try carving the subtask up into different pieces. And by evolving the weights that go from input to output neurons, evolution can tinker with what the robot does under those different conditions. All of those weights are being evolved simultaneously. So evolution is simultaneously trying out different forms of modularity and what should occur under those different conditions. It's pretty difficult for humans to do that kind of thing. Typically, what you might experience yourself doing as a programmer is doing one thing at a time, coming up with classes and objects and a class hierarchy and inheritance, for those of you that are familiar with object-oriented programming, or creating functions in your code if you're not so familiar with object-oriented programming. Thinking about how to break up the problem, defining different functions or defining different classes, and then filling in those functions or those classes, what the code should do under those different circumstances. Evolution is going to do that simultaneously by evolving these two sets of synaptic weights together. Okay, so as I mentioned before, by looking at the differences in abilities of the evolved robots under these 5 different conditions now, we can investigate whether internal units or hidden units, internal neurons, and internal units, this is just a synonym for hidden neurons or hidden units. We can determine whether hidden units are useful. If evolved B robots do better than evolved A robots. We can investigate whether recurrent connections are useful, if the C robots do better than the B and A robots. We can also investigate the role of modularity. So D and E are both modular networks. They have different separate modules that can control the robot under different conditions. If D and E do better than A, B, and C, that tells us that neural modularity is useful in this task. If E does better than A, B, C, and D, that tells us that it's better for us to allow evolution to carve up the task than it is for us to try and carve up the task, at least in this simple example. So far, so good? Okay, it's a lot of build-up. Let's have a look at some results. Okay, so here's evolutionary time measured in number of generations on the horizontal axis. And on the vertical axis here, they're not reporting fitness. We haven't talked about the fitness. Function, but let's talk about what the robot actually does. For each neural network controller, we're going to take the robot and we're going to put it into the arena 15 separate times. So we're going to evaluate each neural network 15 times. We're going to call those epochs. Each time we put the robot in the arena, we're going to put it at a different position and we're going to place it at a different orientation. And in each of these epochs, the robot is going to be allowed to move 200 times. I think I neglected to say it. This is a very early experiment. This was before physics engines. So this was all done directly on the physical. On the physical Kepara. Each controller was evolved for 1,000 generations, like you see here, and they did 10 replications, or they did 10 evolutionary runs for each of the 5 different neural network types, leading to a total of 50 different evolutionary runs. Here's the average performance of the 10 evolutionary runs when we were evolving neural network A. And the vertical axis now is recording fitness as the number of successful epochs. Out of the 15 epochs, how many of them did the robot find an object, bring it to the wall, and drop it outside the arena? That's a successful epoch. You'll notice that on average, after 1,000 generations, the best evolved A network caused the robot to pick up and drop an object outside the arena 6 out of 15 times. You'll notice that B, C, D, and E did better than A. So definitely hidden neurons are useful in this task. And remember, hidden neurons allow nonlinear transformations from sensor values to motor values. That's nice, but that's not so important for our discussion today. You'll notice that E does significantly better than the other 5 early on. Eventually, with more evolutionary effort, evolved B, C, and D networks catch up, but E is definitely more useful, and importantly, more useful than D. Let me just back up here. More useful than D. So allowing evolution to come up with its own way of carving up the task is better than us trying to carve up the task for evolution. Okay. I'm sorry, I misspoke. They did actually use a simulation in this case. So they did do all this evolution in simulation. It was not done in a physics engine. They made their own simple 2D simulator. I forgot that detail. Okay, so all of this was done in simulation. They then took they took the best evolved controllers from the end of the A experiment, B experiment, C, D, and E experiment, dropped them in the physical robot, the physical Kepara, and looked to see how many times the physical Kepara successfully cleaned the arena. So they did 10 replications with the physical Xenobot, with the physical Kepara, and they did this 10 times. And they asked, did the robot clean up all 5 objects in the arena? And this is just more evidence that the evolved E networks were significantly better than the other 4. We're actually going to talk about transferal from simulation to reality quite a bit next week. This is a pretty tricky thing to do in and of its own right, but we're going to save that discussion for next week. Okay, so we can then, we're now going to do a little bit of analysis on the best evolved E network. What is going on? How did evolution carve up this task? What were the subtasks that evolution thought was useful? First question we can ask, is there any correspondence between the evolved modules and what, from our perspective, from a distal stance, as we watch the robot moving around in the arena and cleaning it up, is there any obvious correspondence? So is this neural module in control when the robot is looking for an object? And is this module in control whenever the robot has an object? As you're going to see in a moment, there is no obvious correspondence, at least none that anyone has been able to find. You might be the first one to find any, but I've had hundreds of students and hundreds of investigators have read and studied this paper. No one's been able to find a correspondence yet. I'm going to show you those results in a moment, and you can come to your own conclusions. Let's talk a little bit about this single evolved E controller. It only has 2 states. What do I mean by that? What I mean is that in the case of the right motor neuron, there are times in which the right selector neuron is larger than the value of the left selector neuron. meaning this circuit is in control. And there are other times while that robot is moving around in the arena where the left selector neuron has a greater value than the right selector neuron, meaning this circuit is in charge. In the other three clusters, there is no switching between the pair of selector neurons. Evolution elected not to use modularity in these parts of the network, only in this part of the network. So far, so good? Okay. Okay, so let's have a look at this evolved robot in action. Again, this is a very early experiment. They unfortunately did not take any videos of the robot operating in this case. The robot was placed in the arena at this position here, and this trace, this line, this trajectory here reports the movement of the robot. There were originally 1, 2, 3, 4, 5 objects placed at those positions in the arena. You'll notice that 3 of the spots are now empty, and there are now 3 objects outside the arena. So the robot successfully grabbed and got rid of this object, grabbed and got rid of this object, grabbed and got rid of this object. And if you look carefully, you can kind of see how it did it. So if we start here, it's hard to see exactly where the robot went, but it grabbed one of these objects and faced the wall, dropped the object, turned around, started driving in this direction, probably grabbed this object, got to the wall, dropped it out here, went here to the wall but didn't drop anything, came back, grabbed another object, went to the wall, dropped this object. It's a little hard to follow exactly what it did, but I think you can hopefully get the idea. The robot never managed to grab or get rid of these 2 objects. Okay, let's now have a look at the results down here. Each row here is trying to report some aspect of the robot's behavior. I'm going to start with some of the easier ones to understand first. Let's look at the light barrier one. In this case, they wrote light barrier in English, not Italian. Remember, this is the little laser beam between the 2 pincers that make up the robot's gripper. You'll notice that that light barrier is unbroken for a period of time. I'm sorry, I forgot to mention. The horizontal axis here, this is not evolutionary time. This is the amount of time in seconds that the robot spent in the arena. We're playing back one evolved neural network. So for the first few seconds, the light barrier was unbroken, and then suddenly the barrier was broken and stayed broken for a period of time. Then the light barrier was unbroken again. Then it was broken for a period of time. So we'll notice that there are these contiguous blocks of time during which the light barrier was broken. What do you think the robot was doing during those 3 time periods? If you have an idea, go ahead and type it into chat. As Alex says, the robot was gripping the first object, then the second object, then the third object, right? That's pretty straightforward. Okay, let's jump around a little bit. Let's have a look at LM, RM, PU, and RL. These correspond to the four values of the output neurons. And remember, there's different output neurons here. So we're just reporting here the value of the 4 motor neurons that were actually connected to the behaviors at that time. Here's the value of the left motor neuron, the right motor neuron, the pickup neuron, and the release neuron. You'll notice the release neuron has a high value for quite a while, and then the release neuron value drops to basically 0. It's at mostly 0. So the value of the release neuron is being inhibited during the time that the light barrier is broken, which makes sense. Evolution has evolved synaptic weights that inhibit the release neuron when the light barrier sensor is broken, right? We do not want the robot doing this when it's holding the object. At least not until it gets close to a wall. We want it to hold on to that object until the robot is facing a wall, and then it can do this. RL is similarly suppressed in the other two periods of time during which it's holding an object. You'll notice that there are little spikes of activity at the beginning of each of these three periods. This is the pickup. This is the pickup behavior. So here's the robot picking up the first object and then inhibiting release and also inhibiting pickup. And at this point in time, right at the end here, release is no longer inhibited. You'll notice at this period of time, if we drop down to these rows here, we have I1 through I6. What's happening at around this point in time? What does I1 through I6 mean? Any ideas? You'll notice that at this point in time, 2 and then 3 of the I values here are high. What's I1 through I6? Well, it says right here. These are the infrared sensor values. You'll notice at the beginning of this, they're triggered, right? Exactly as Andrew says here, they're triggered. You'll notice at the beginning of the pickup period, I3 is pretty high, but I2 and I4 are low, relatively low, and I1 and I2, I5 and I6 are not firing at all. So this period, from the robot's point of view, or this situation looks quite different from this situation. At this situation, this is the robot facing the wall. More of the infrared sensors are being broken, compared to this situation where only 1 and maybe 2 or 3 are firing. So the robot, by looking at I1 through I6, it can distinguish between, am I in front of an object or am I in front of a wall? Am I in front of a wall? More of the sensors are, infrared sensors are firing. So when a lot of the eye sensors are being tickled by the wall, and the light barrier sensor is broken, so the robot is holding an object and it's in front of a wall, release is triggered. The robot lets go of the object. Okay. LM and RM, these are the values controlling the motors. So you notice the left motor is spinning quite a bit. The right motor is on most of the time, but it's stuttering off a little bit. And then during this period, both motor neurons are being inhibited more. They're slowing down and stopping. This is the period during which the robot is facing the wall. So the robot is learning to stop near the wall and eventually release the object. The moment it releases the object, it stays there for a while. So here's the robot. It's already dropped the object. It's standing in front of the wall. The motors are not firing very much, but eventually they start firing again and off the robot goes. Okay, let's have a look at W and T here. So this is sort of what is the robot perceiving. These values here, these are all coming directly from the robot's sensors and motors. These values here, these were written down by the investigators. Was the robot in front of a wall or target? The target object. So wall, target object, wall, nothing. Driving around looking for an object, wall, target, wall, target, and so on. Mod up here, mod is meant to represent which module controls the right motor. As I mentioned before, the relative values of the two selector neurons assigned to the right motor, they are altering. One of them is higher than the other from time to time. But in the other cases, it's always one that's higher value than the other. This is reporting when the robot is switching from allowing one module to control the right wheel, and then the other neural module being allowed to control the right wheel. Okay. So if you look at the black stretches here, this is one neural module controlling the right wheel. The white stretches in here represent periods of time during which the right neural module is controlling the right wheel. Do those periods of black and white correspond with particular situations for the robot? Not that I can see. We would expect that for example, it could be that whenever the robot is holding an object and trying to get rid of it, we have black up here. Whenever the robot is looking for an object, we have white up here. That would represent that these evolved modules have carved up the task into holding an object or looking for an object. That does not seem to be the case. The investigators made this easier for us by drawing these rows down here, which correspond to different situations. So if we look at row A, this is carving the task up into carrying an object and looking for the wall. So here's the robot looking for an object. Here's the robot carrying an object, looking for an object, carrying an object, looking, carrying, looking. If you jump back and forth between A and mod, you can see there's no clear correspondence. So however the evolution is carving up this task, it is not based on whether or not the robot is carrying an object. B is basically the same thing, just kind of flipped around. Gripper is empty, or gripper is empty and looking for an object, or not. C is yet a different way of carving up the task. The robot either sees something, which could be a wall or an object, or it doesn't see anything. That's C. You'll notice in C, most of the time, the robot sees something, but there's periods where it doesn't. Again, if you jump back and forth between row C and the mod row at the top, there isn't really a clear correspondence. And so on and so forth. One potential candidate, there is one potential candidate in here, which I think C is the closest one. I think C is the closest one, but again, not perfect. Okay, so what we can conclude from this study is, again, that evolution has carved up this task into subtasks, but not any subtasks that are intuitive to a human being. Okay, I ask this question every year. Am I missing anything? Can anybody see a combination or some other way of carving up this task that makes sense here? Can anyone see how evolution is carving up this task into subtasks? Do the black periods up here correspond to particular combinations of sensation down here? There's a little bit. If you look at the infrared sensors as a whole, you notice when the infrared sensors are firing, it tends to be dark in the mod row and vice versa. But other than that, not much of a correspondence. Okay. Last thing we're going to look at in this experiment is not so much about modularity, but another aspect of evolved behavior which is important. The investigators started by asking this final question in this paper. When the evolved controllers are placed back into the robot after evolution, and the robot is placed in novel locations, how many errors are made? This is a big issue for robotics and AI in general. We can train our robots and AI all we want in the lab or train autonomous vehicles on the road. But what happens when our trained machines encounter a situation they never encountered during training before? How will they behave? Okay. So in this case, they were pretty extensive. They took evolved controllers, dropped them back in the robot, and then placed the robot near an object or the wall at 180 different angles. So they placed the robot facing the wall, for example, but also minus 90 degrees, head on, plus 90 degrees. So 80 different angles towards the wall or towards an object at 20 different distances away from the wall or the object. And they placed the robot at either starting with holding an object or not holding an object. So that yielded a total of 180 different angles, each at 20 different distances away from an object or the wall, and either full or gripper empty, led to a total of 7,200 trials. You'll notice then that out of those 7,000 trials, for each of these evolved networks, they reported on the vertical axis the number of times out of those 7,200 trials that the robot made a mistake. What's a mistake? If the robot was placed near the wall, facing the wall, and its gripper was full, we know what the robot should do in that case. It should drop the object. If the robot was placed near an object and its gripper was empty and it's facing that object, it should grasp that object. So in each of these 7,000 trials, we knew exactly what the robot should be doing, and they just labeled each of those trials with a binary value. 0, it did the right thing. 1, it did the wrong thing. I don't know why, but for some reason they did not report the results of network C. I don't know why that happened. But anyways, so most of the time the robot did the correct thing, and in a few cases the robot did the wrong thing. Okay, I like this plot better. This is a better way to evaluate this. We're actually going to look at 2 different evolved E controllers. Here's the results from one evolved E controller. Here are the results from a second evolved E controller. On the horizontal axis here, we're plotting the position, the angle of the robot relative to the wall or an object. The vertical axis represents how far away that robot is from the wall or the object. Very close to the wall or object, very far from the object or wall. We can then, each pixel then represents a particular starting angle of the robot and distance from the wall or the cylinder. We can then do this again each of these 4 panels corresponds to 4 different situations. The robot is facing a wall and its gripper is empty. The robot is facing the wall and its gripper is full. The robot is facing a cylinder and the gripper is empty. The robot is facing a cylinder and its gripper is full. Okay. In each of these 4 panels, a particular pixel the color of that pixel represents what the robot did at that angle relative to the wall or cylinder, and its distance from the wall or cylinder. White means neither pickup nor release was triggered, which is most of the time. Black pixels correspond to triggering of the pickup behavior, and gray pixels represent triggering of the release behavior. Let's start down here. This is the case where the robot is being placed near to a cylinder and its gripper is empty. What does this small group of black pixels down here tell you? What does this panel as a whole tell you about what the robot does when it's placed near a cylinder and its gripper is empty? Any ideas? So this small Logan says it picks up the cylinder only when it is placed directly in front. So that's the 0 here, right? It's facing more or less directly onto the cylinder, and it's very close to the cylinder, right? So that makes sense. This robot is doing pretty much what you would expect it to do. In the higher regions of this panel, if the cylinder is too far away, the robot doesn't try and grasp it. And in the far left and the far right regions of this panel, the robot is facing too far, is angled too far to the left or angled too far to the right from the cylinder to be able to grasp it, and it does not attempt to do so. Tell me about this cluster of gray pixels up here. What does that tell you about this particular robot's behavior? This is the situation where the robot is being placed near a wall and its gripper is full. What does this panel tell you about the robot's behavior under those conditions? Missy says it only releases when it's facing the wall, right? This is the midline of the panel, and is very close to the wall. Yep, exactly. Alex says the gripper releases when the robot is close to the wall but slightly angled. You'll notice when the robot is placed face on at 0 here, it's facing directly to the wall, and it's also very close to the wall. It doesn't release the object. Kind of interesting. It's not necessarily a mistake. As long as it actually does release it, that's fine, but kind of interesting. Let's now jump down here. This is a second evolved E-controller. We again placed it back in the robot under lots of different conditions, and when the robot is close to the wall and its gripper is full, it, gray pixels, releases the object. That's good. When the robot is close to a cylinder and its gripper is empty, in a lot of cases it grasps the object. That's good. This is not so good. This is the case where the robot is placed near a cylinder and its gripper is already full. So it's already holding an object, and there's another object nearby. You'll notice that if the robot is angled a little bit, to the right of the object, and it's pretty close to the object and it's already holding something, it will release the object it's already holding. So this is a mistake down here. I'm now going to jump back and forth between these two slides. And in the bottom panel here, I'm showing, this is for this second controller. This is showing all the situations that controller encountered during evolution. Black means the robot experienced that situation, and white means it did not experience that situation. If you'll focus on the little gray triangle down here, you'll notice that set of conditions, that set of conditions was never encountered by the robot during evolution. So this, if we were to release the robot in the wild after evolution, this would be surprising to us. The robot has never encountered this situation, and we didn't realize this during evolution because it never happened, but there are certain conditions under which the robot will drop a cylinder that it's already carrying if it approaches another cylinder in just the right way. It's a small mistake. Most of this is white, and where we see black and gray is where we would expect to see black and gray, but this is not a perfect robot. One of the disadvantages, Missy says, like when my dog can't choose between two tennis balls. Possibly, yes. Dogs never encountered tennis balls when our ancestors were evolving them from wolves into dogs. So maybe yes. Animals and humans, you've all had this experience. You don't often know what to do in situations you were never trained or taught what to do that you'd never experienced before. For a little Kepra moving around inside a little small arena, maybe this doesn't matter. This matters a lot when we're talking about an autonomous vehicle that detects a pedestrian in the street, and that pedestrian is in a position in the street relative to the car that the car never experienced during training. Then it becomes deadly serious. How do we ensure that our machines operate perfectly? Do we as a society want to regulate our machines, that we will never allow them on our roads or allow them in our airspace unless they are proven to be perfect? If our society chooses to do that, we will probably never deploy autonomous machines. We have already started deploying autonomous cars and autonomous aircraft. It's already begun, and we know for a fact those machines are not perfect. This is a massive technological challenge that our society is going to have to grapple with in the years to come. It is also a regulatory and social and political issue we are going to have to grapple with in the years to come. Okay. All right, so just to conclude this experiment was a success in the sense that evolution proved that modularity is useful, and evolution should be in charge of determining how to carve up the task. In the case of the E network, what exactly did the evolutionary algorithm figure out? It figured out which sensor states would be experienced while moving. The robot didn't experience every possible situation it could. We could evolve our autonomous cars and our autonomous drones to have rich experiences, not just to perform the task, but to seek out all possible situations that machine can experience and still successfully perform the task. Evolution determined whether modularity was useful at all. It evolved the usage of the selector neurons. It didn't necessarily have to use the selector neurons, and actually in 3 of the 4 cases, in the one we looked at, it doesn't use them. Evolution, by evolving the sensor to selector neuron synaptic weights, evolution shaped what situations would trigger switching between different neural modules. And by evolving the synaptic weights that flow from the sensor to the output neurons, evolution was also simultaneously determining what the robot should do under those conditions. Okay, that's quite a bit for today. We got 4 minutes left, so we're just going to start in on lecture 14 today, unless there's any last minute questions about modularity. In this challenge here, we're going to talk about what the challenge is in a moment. The solution to that challenge is a very popular method or pair of methods in the literature now, neat and hyperneat. Before we talk about neat and hyperneat, let's talk about the problem that neat and hyperneat were evolved to solve. This is still more or less an open problem in the field of neural networks and robotics. It is known as the competing conventions problem. Let's go back to remembering the toy neural network that solved the XOR problem. We have an input down here, and we have a single output down here. In this case, I've taken this figure directly from the paper, so it's flipped upside down. We have sensor neurons down here, 3 hidden neurons in the middle layer, and 1 output neuron over here. Let's assume that this network has already been evolved to perform some task. It's not strictly XOR, but let's imagine it's a task in which the neural network needs to compute 3 partial values, or it needs to compute 3 intermediate functions, A, B, and C. You may remember when the neural network was computing the XOR function, it needed to compute AND and OR, and then combine the results of AND and OR for the final XOR result. In this cartoon example here, imagine that it needs to compute A, B, and C, and then correctly combine A, B, and C into the result that is sent to the output neuron. Let's imagine that this neural network is evolved and it's almost perfect, but not quite. It's getting almost B, almost A, almost B, almost C, and almost the correct output neuron. Remember, in the case of the XOR function, the network needed to output 4 different values under different conditions. Let's imagine this network gets 3 out of the 4 correct. It's almost perfect, but not quite. Let's imagine elsewhere in the population of evolving neural networks, let's imagine these 2 neural networks are in the same population. This one has also evolved the ability to compute subfunctions A, B, and C pretty well, and combine them pretty well to produce the desired output. Okay. Let's imagine now that this network has evolved A correctly, B correctly, but is not doing such a good job at C. On the other hand, this neural network is computing C very well, but not A and B. So this one is doing A and B. This one is only doing C. Wouldn't it be great if in this population we picked these two neural networks to be parents, we cut them in half, and we glued the two halves together to produce a new child neural network? If parent 1 is doing A and B well, and parent 2 is doing C well, it would be great if we could cut them and take the good A and B from parent 1 and glue it onto the good C from parent 2. I want you to imagine taking a knife and cutting through these networks, and you need to cut in the same direction through both networks. So you can cut here and here, or you can cut here and here, or you can cut here and here, and glue those two pieces together. We're out of time, so I'll leave you to try and, I'll leave as homework this mental exercise to see if you can find a way to cut these and glue this A and B onto this C. You have a quiz due tonight. You're working on assignment 9. I wish you a good rest of your day, and we'll see you all back here on Thursday. Thanks very much, everyone. Bye-bye.